to my today's lesson, and I want to again just proceed from where I had left in my last discussion in as far as carbon and its compounds is concerned. And if I can be able to make myself very clear, I had begun discussing this topic, and I had left at the allotropes of carbon, and the last allotrope I was discussing was diamond, if I can remember very well. And in this case, I had actually begun looking at the physical properties of diamond. I had first said that diamond has a shiny appearance, or it has what you call a characteristic luster. Good, the short form of characteristic. So a characteristic luster. So this is to say, if diamond has a shiny or characteristic luster, then it means it has what you call a high refractive index. Obviously, you'll be able to actually refer this to N. So in physics, refractive index gets abbreviated as N. And what is refractive index? You see, it's just a ratio or the relationship between the speed of light in empty space. The speed of light in empty space in relation to the speed of light through a particular medium. Good. The speed of light in empty space over the speed of light through a medium. So let me say this is a container and this is water. Then what is refraction? The speed of light in empty space. Good. The speed of light through a medium. That can be a very good example. So the bending of light. Look at that. The bending of light as it travels through the space and then through a medium. It travels from one medium to another. So the bending of light as it travels from one medium to another. The speed of light through an empty space and the speed of light through a medium like water. So the speed of light through an empty space over the speed of light through a medium. Okay, I can proceed to something else. So it has what we call a shiny or characteristic luster. So that means that's what we call a high refractive index. That is to say, the speed of light in empty space over the speed of light through a medium. That means it has the ability to actually make the light to get refracted away. You see, it has actually a high refractive index. When the light falls on it, it gets refracted away. So it actually looks so shiny, or it has a characteristic luster. Or you'll find most people actually using this aspect of it as a high optical dispersion. When light falls on it, it disperses that light away. So it has what we call a high optical dispersion. Something else apart from being shiny and having a characteristic luster, diamond is also transparent. And you'll find people saying it is colorless. So it's actually transparent, not black and opaque the way graphite looks like. So it's actually transparent. And of course you can say colorless for that matter. Transparent, colorless, shiny appearance. Diamond has a high melting point and boiling point. Why? Because I've said diamond majorly has carbon, which is actually having an electron configuration of 2 to 4 in as far as its position in the periodic table is concerned. Something fun with the diamond is that it uses all its 4 electrons in bonding. Look at that. All its 4 electrons in bonding. So every carbon atom is bonded to actually 4 other carbon atoms. So there are very strong covalent bonds between the carbon atoms. Look at that. Very strong covalent bonds between the carbon atoms. So the strong covalent bonds between the carbon atoms, which are actually having what we call a uniformity, will make this compound require very high temperatures for these strong covalent bonds to be broken. What is a covalent bond? A bond between 2 elements such that there's equal sharing of electrons. Good. So So the 4 strong covalent bonds require very high temperatures to get broken. That's why diamond ends up having very high melting and boiling points. Something else is that you have to also consider this aspect of solubility. And I want to actually introduce to you this. You should note that diamond is insoluble. Diamond is insoluble in water, but very soluble in organic solvents. Insoluble in water, but very soluble in organic solvents, which are non-polar. So insoluble in water, but again soluble in organic solvents or non-polar solvents. Some of these non-polar solvents are like carbon 4 disulfide, or you can talk about methyl benzene or trichloromethane or benzene, or even other very complex compounds that get manufactured in the industries. You see, we always say in chemistry that a polar substance can only dissolve in a non-polar substance under witchcraft. That is to say, a polar substance cannot be able to dissolve in a non-polar solvent. So a polar substance cannot be able to dissolve in a non-polar solvent. Look at that. A polar substance cannot dissolve in a non-polar solvent. But a polar substance can dissolve in a polar solvent. Good. I had actually explained this in my last video, and I do not want to repeat myself. I had given an example of, let me say, for example, if you have sodium chloride, this is a polar substance. It is partially positive and partially negative. This polar substance, which is partially positive and partially negative, cannot dissolve in a non-polar solvent like methyl benzene, which is actually not partially positive and partially negative. And if I have a polar substance like sodium chloride again, which is partially positive and partially negative, it can be able to dissolve in a polar solvent like water. And of course, water has 2 molecules of hydrogen and 1 molecule of oxygen. So if it is partially positive and partially negative, look at that, it can dissolve polar substances which are also partially positive and partially negative. So water gets called a polar solvent because it is partially positive and partially negative. So diamond is a non-polar substance. It cannot dissolve in water. Water is a polar solvent. So diamond, being a non-polar substance, can only be able to dissolve in non-polar solvents like carbon 4 disulfide and methyl benzene or trichloromethane or benzene. Okay, so that is actually briefly well explained, and it's good that you note that this diamond is a poor conductor of electricity. Why? It has no delocalized electron. You see, it has no mobile electron. It has no free electron. It uses all its 4 valence electrons in bonding. So no electron left at this point makes this diamond a poor conductor of electricity. Compounds, for example, metals are able to conduct electricity using their mobile electrons or their delocalized electrons. Some compounds which are ionic use their mobile or delocalized ions when they are actually in molten state or in aqueous state to conduct electricity. And of course, we always say graphite is the only non-metal that can be able to conduct electricity, but all other non-metals are actually poor conductors of electricity. So carbon, in as far as diamond is concerned, does not have any mobile electron, so it's actually a poor conductor of electricity. So it cannot conduct electricity because it has no delocalized electron that it can use in conducting electricity. But it is actually a good thermal conductor. A good thermal conductor. Why? You see, if you look at the structure of diamond, each carbon atom is bonded to other 4 carbon atoms with very strong covalent bonds. These carbon atoms are arranged in a regular manner with uniformity in as far as the covalent bonds are concerned. This gives what you call a regular array or a crystal lattice, or what you call a regular tetrahedron structure, which is very giant. So in that case, there are so many covalent bonds that get used in bonding many carbon atoms together to give what you call a regular tetrahedron structure in as far as diamond is concerned. So the hardness of diamond, as far as the covalent bonds are concerned, makes this substance to be able to absorb more heat and be able to retain that large amount of heat. That heat can be able to actually get used in making it a good conductor, because the particles in diamond are closely packed. See, when they get closely packed, it becomes a good conductor of heat. Okay, so that is actually just a brief summary of the physical properties of diamond. A brief summary of the physical properties of diamond, and maybe to look at the uses of diamond. Diamond has quite a good number of uses, and you'll be able to actually understand that one, it's actually a very common gemstone that gets used in what we call jewelry because of its sparkling nature, and in this case it is actually used in making jewels, you see, and this is because of its high refractive index or its high optical dispersion, and because of its shiny appearance, it actually gets used in making jewelry. So that's actually one of the uses of diamond, a very important gemstone. Number two, the hardness of diamond has been applied in ensuring that it gets used in making drilling parts of drilling machines, those that can be able to drill boreholes. They get used in construction sites. They are used actually in road construction. So the end tips, the drill bits that get actually used in drilling boreholes and other parts, and as far as construction is concerned, are made of diamond. It's because it's actually a very hard substance naturally as far as our existence on earth is concerned. The hardness of diamond can as well be able to get applied in trying to explain to us how glass cutters can be able to get made. So the apparatus or the instruments used to make whatever gets used in cutting glass is made of diamond, and it's because of its hardness that makes it possible for us to use it as a glass cutting raw material in as far as the machines that get used in that purpose are concerned. So it's used in glass cutting purposes. It is a colorless substance which is transparent, of course, and that can be able to actually explain itself. You see, it is actually also important for you to note that diamond is a good thermal conductor. So in areas where very high temperatures are required, and as far as heating is concerned, it can become very, very applicable because it is very hard. The particles in it are very closely packed. That requires now us to use it in what you call thermal conducting areas because of its ability to absorb a large amount of heat and retain that heat. So heating becomes easier for us in as far as now applying the aspect of diamond with its hardness is concerned. Now that is all about diamond. I'll want to go to graphite. Now if I look at graphite, I must have to understand that now again it contains carbon, and in this case the electron configuration is again 2 to 4. But in this case you'll find that graphite, in as far as its structure is concerned, does not use all the 4 valence electrons in bonding. It only uses 3 electrons. So that means it has 1 unshared electron. 1 electron becomes delocalized, 1 electron becomes free or mobile. So let me just make a sketch of graphite. For example, I can have something of this sort. This is the first atom, the second atom, the third atom. So 3 electrons are used. 1 electron remains unused. used. So the structure can extend to this end, that end, that end. So what is this? This is what you call a hexagonal structure. So graphite has what you call a hexagonal structure. So this can be one plane of graphite. See, the structure of a graphite plane, where it's actually showing us that it uses only 3 electrons in bonding. So it does not use all the 4 electrons in bonding, it uses only 3. So 1 electron remains unshared in as far as its structure is concerned. And this structure is actually hexagonal. So we have 1, 2, 3, 4, 5, 6. So 6 sides, hexagonal. A hexagon is actually a structure which is regular. It has 6 sides. So graphite has what we call a hexagonal structure. So just in case you have so many planes of the same allotrope of carbon, we may have something again here also, like this. Just making a sketch. Good. Very good. So you may have something of this sort. Look at that. So you see, one plane of graphite can get attached to another plane of graphite by what we call weak van der Waals forces of attraction, or the intermolecular forces of attraction, which are very weak. So they are called weak intermolecular forces of attraction, or van der Waals forces of attraction. So here, one layer of graphite is attached to another layer of graphite by the van der Waals forces of attraction, or the weak intermolecular forces of attraction. But now between the carbon atoms, we have what we call the strong covalent bonds of attraction. In the carbon atoms, strong covalent bonds of attraction. And now between the layers, we have what we call the intermolecular forces of attraction, which are very weak. So these are just the carbon atoms. Good. They have strong covalent bonds of attraction between them, but between the layers, we have what we call the weak van der Waals forces of attraction. So this is just a simple structure of diamond. It has what we call hexagonal plates, and each structure will differ so much from that of diamond. You see, the atoms are arranged hexagonally, and that will form what we call flat layers. You see, it will form what we call flat layers. So each carbon atom is joined to other 3 carbon atoms, and 1 atom remains unused. So it's actually able to have what we call very strong covalent bonds between the carbon atoms. So it's actually, again, relatively strong and rigid. But the force of attraction between the adjacent layers are very, very weak, or relatively small. Now, what are the physical properties of graphite? Number 1, it is actually soft. Why? Because between the layers, we have what we call the intermolecular forces of attraction, which are very weak.